All right, I'll begin with a word of prayer. I will begin with a word of prayer. Dear Heavenly Father, we thank you for this day. I thank you for the weekend, and I just pray that you'd help us to use this time wisely to answer any questions that might still remain about this material, Lord. In your name I pray, Lord Jesus. Amen. So, I assume all of you who want to... Aw, man, I got no juice. Sad. Oh man, look at that.
Picked a very nice marker today.
It's all with the
Rats. All right.
You listen to Weird Al Yankovic?
Oh yeah. Yeah, I was showing my kids some classics yesterday. We could watch one. No. Probably that won't help you with the test, but I don't know. Like that might be a good challenge. Can I make a series and can I make a Power Series application for a Weird Al song? I mean, there's a vast catalog of these things at this point.
Or questions?
Oh, I mean Weird Al songs. There's what, like 100 of them? I don't know. Okay, so the first, I will post this eventually. But yes, sir.
Before the test, you're going to post like today?
Yeah. So, of course I gave this to you guys, so it's not like these are secret or anything, but, and I think I posted the solution to the first three problems, didn't I? Didn't I post the solution to quiz 7? Yeah. Okay, so, let's see here. Let me skip past the, these are just, I just put the answers. I will say this before I get carried away, like problem 4, I think that's right, but Wolfram Alpha has made me doubt because, well, this is like too hard for Wolfram Alpha. This problem is one of those ones that's just a little bit in the danger zone. Well, one of the things that makes this problem really funny is it's not strictly speaking an alternating series that converges in the following technical sense. I mean, yes, it does converge, all right, but the funny thing about that problem, and so I was thinking, oh look, the first term is smaller than 0.001, so we're done, right? But what's the deal with the terms in this sequence? Are they decreasing? They are not. Well, I mean, they start decreasing after here. So like I can apply the alternating series estimation theorem beyond here, but I can't apply it to the first term, which is where I'd like. So like one of you got fished into that, which is understandable. But I think that if you sort it out, you got to go with the first 4 terms by my estimation, because when you get to n equals to 5, the size of the term is smaller than 0.001. So we got to go at least to n equals to 4, which gives you this. And if I punch the numbers into my calculator correctly, this is what that works out to. But I'm a little bit, and a couple of you got this number approximately. Some of you were too careless with the arithmetic for me to tell if you're right or wrong, you know, because this is really fussy. So listen, before I forget, I put a couple of bonus problems at the end of this. They're not really bonus, but just extra problems. So like extra problem 2 here, this is a far more reasonable version of this kind of problem. So the thing I should remember to do on the test if I ask one of these is to make sure my upper bound is not 1. Because if I make the upper bound like a fraction less than a half, less than 1, then when I plug that into the, the power functions, that also gets like super tiny, super fast, which makes, computation of, the integral to within a reasonable error much more like computationally accessible. You do need a calculator for tomorrow's test. So please do not come to this test without a calculator. Be sure you have a calculator, because this kind of thing could be on there, and I am looking for, some amount of numerical, what do they say, number sense? So any questions about any particular problem in here? Yes, sir.
Can you do the limit question?
The limit question. So, yeah, so the derivative of the inverse hyperbolic sine is 1 over the square root of 1 plus x squared, right? Well, you may or may not know that, but once you have that, then you can go binomial on that thing, right? So the binomial series with alpha equal to minus 1/2, there's the first. I don't even need, I think all I used is like this in the end product. Like only the first term actually mattered. But I did it for 4 terms just for the sake of showing you. And so here's integrating back, I get that. The constant term is 0 here. There was another problem which didn't have a constant term of 0, and some of you missed it. Ooh, let's see here. I realize that I've been sort of ingraining in you the sense that the constant term is always 0, but that's just a quirk of our example set. Anyway, so I then took this and I did a substitution with x to the 5th, right? So I've got like x to the 5th minus 1/6 x to the 5th. This stuff doesn't matter. It doesn't matter. And then this one expands to 1 plus 1/2 x squared minus 3/8 x to the 4th plus dot 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 dot. I've actually done this one, give or take, before. When I look at the gamma function for relativity, it's essentially the same. Okay, there's a minus 1/2 instead, but whatever. Anyway, so multiplying this out, the Maclaurin series for this guy, here's the first 3 terms. All right. Now I'm asked to take the limit of, you know, this monstrosity, minus x to the 5th. That's the leading term here, right? And then the next to leading term is x to the 7th. That survives, of course, well, x to the 7th over 2. So this kind of division, you don't need to do long division for, right? That's something I should have said at some point. We've done it, but let me say it again. If you're just dividing by a monomial, you don't need to do long division, right? You can do this kind of division term by term. Okay, so like, what the, oh, sorry, I didn't see this. Maybe I should have put that at the start, you know? Anyway, those cancel, and you're left with x to the 7th over x to the 7th, which is 1/2, because there's a half there. And so the answer is 1/2. I think 2 groups got this. And then others did not. Some will never know what would have happened for you guys did not try. I would encourage you to figure out how to do these kind of problems. The likelihood of there being one, I wouldn't say like this, but like this. I mean, there should be something like this on the test. I don't know if it's going to be exactly this one, but something that involves this skill set should be on the test, yeah. It could be inverse hyperbolic sine. Could be inverse hyperbolic cosine. I do want you guys to know the calculus of these things. So, if you forgot the derivative of inverse hyperbolic sine, how do you derive it? Let us review. Y equals to inverse hyperbolic sine. Take the sinh of both sides. Differentiate both sides. Chain rule. What's the identity for cosh and sinh? Well, remember, cosh squared y minus sinh squared y is equal to 1, which is actually giving me cosh squared y is equal to 1 plus x squared, because sinh is x. And so this is 1 over the square root of 1 plus x squared. There's no ambiguity here because hyperbolic cosine is strictly positive, right? It's in fact larger than or equal to 1. And so there you go. That's why the derivative of inverse hyperbolic sine is what it is. This is not something you shouldn't be able to derive. I don't have to memorize it because I can do this in 3 minutes. 1 minute, 30 seconds, I don't know, whatever amount of time that was. Yeah? And you can do the same thing for like inverse hyperbolic cosine, right? If you don't know this one, you could work it out. Oops, cosh of y equals x, you know, sinh y dy dx is 1, so dy dx is what? 1 over sinh, but this is a little bit different. Since I get x squared minus 1, so 1 over the square root of x squared minus 1. I can choose the positive square root because sinh is always increasing because its derivative is hyperbolic cosine, which means that it's a positive, has a positive derivative everywhere, so there's no ambiguity in the choice of sign. There you go. That's the derivative of, I think. Other way around. Wait a minute. Yeah. So, is that right? That feels wrong. That feels wrong.
It should be, the derivative should be 0. That's right.
What's weirding me out is like, oh, see, here's the problem, and here's why it's not a problem. I'm thinking about this formula. I'm seeing that this blows up at x equals plus or minus 1, right? But then I think about sinh. Does sinh blow up anywhere? Excuse me, does cosh blow up? Does inverse? Well, that's weird to me. Like, cosh shouldn't have any kind of, But here's the thing. Do you ever get to x equals to plus or minus 1? Remember here, x is in the domain of the inverse hyperbolic cosine, right? Which is the range of cosh. The range of cosh is 1 to infinity. It only reaches 1 at 0, and that's where the hyperbolic cosine has a horizontal asymptote. What happens with the inverse function? What is a horizontal asymptote? It becomes but horizontal tangent. A horizontal tangent becomes a vertical tangent for the inverse function, and that's what's going on. Does that make sense? And this only touches 0 when you're getting, like, what I'm trying to say here is this is for x, an element of 1 to infinity, okay? So only the 1 is problematic, and it's not really a problem, it's just well, there's a vertical tangent for the inverse hyperbolic cosine. Or that's well, anyway, let me shut up. I'm now getting far afield. Let's go back to the test. Any other questions?
Can you show us
9? Which one am I on right now? This one. 9's not bad. You just so I would say the thing that struck me the most as I was solving your homework is that there were a lot of problems where you could solve with just Taylor's theorem, and I can definitely make problems which are just not good for Taylor's theorem, right? It's not hard to do that, but this is not one of those. So here, since you only need the first 3 terms, it's not too much trouble to take 2 derivatives of that function, right? Then I plug in and apply Taylor's theorem, and there it is. So, other questions? Problem 10. Problem 10. I would say problem 10 is a good example of a place to not do Taylor's theorem, right? You definitely don't want to be differentiating x to the 11th over cosine of x to the 4th even once. Like, you just don't want to, right? At least I don't. And but this is pretty much tailor-made for. Now, of course, I've divided 1, right? And then later I multiply back through the x to the 11th. But you could just divide x to the 11th into it if you'd rather, right? You got different ways you could go here. You don't have to. I have this habit of setting aside like x to a power when I'm finding a Maclaurin series and just coming back to multiplying it because multiplying is easy, But let's see here. See, I multiply the x to the 11th at the end, and then. So I don't know what happened. Like, a lot of people didn't have, like, some of you, like, I think about half of you had this right, and the other half of you, like, I don't know what happened. Something happened, like the last step or something. The coefficients are off, the powers are off. Like, there's just a certain carelessness at the end, which is unfortunate because I think you did the hard part, which I would say is the division, more or less correctly, right? Let's see, what else can I show you? Oh, the last problem. So at least, I think 2 groups got, well, maybe one or two groups got this right. I'm not sure if two got it right. So the way to work this kind of problem is to identify, you know, coefficients which are of the same type, right? And so here, this is kind of like a Larry Moe Curly type problem in terms of it's got the triplicity, right? And so you've got things of the form 3j plus 1, 3j plus 2, 3j. 3j plus 3 can be lumped into the 3j terms, right? So these are both essentially multiples of 3 powers. So I can combine, by making a shift of the index here to n minus 1, I can combine this and the last one together. And so here I just FOILed out the x plus 1 cubed. That's where these 3's come from. Those two terms in the middle are kind of by their lonesome. Anyway, so I get this. And then, since power series have to be equal order by order, I can equate the constant terms. I can equate the multiples of 3. I can equate the multiples of 3 plus 1. I can equate the multiples of 3 plus 2. These are the equations that you get. Now, of course, you could go about trying to solve these, you know, if you were given a particular A. And of course, you can't just be given any old A, right? I mean, A is not free. You can't just make it anything. Because, like, what does this say? This says the 3k plus 1s and the 3k plus 2s have to match up. They have to be equal because they're both joined by this 3bk, right? So there's like that. So this is, you know, there's a complicated interrelation between these three series. But that's how you'd link them. Anyway, the point of this problem was to see if you could switch an index and use this idea of equating like coefficients, which we've come across a few different places. Mostly it's been in the context of even equals even, odd equals odd, but we also have this triplicity. And you could do fourplicity, right? I mean, you could split the index in a lot of different ways, right? Like, you could have, here's a stupid example. Sum n equals 0 to infinity of a n x minus x naught to the n, right? And you could have equal to, I don't know, n equals to a sum of decimal representation of pi truncated digits, you know? We call this thing Pac-Man, and not an element of Pac-Man. My point to you is it doesn't have to be even or odd. It doesn't have to be triplicity. Just any logically distinct collection of indices, one for each order, you can equate. Because you can equate order by order. So like it, you know. That's a ridiculous example, but I'm a ridiculous person, so there you go. You get what you paid for. Yes, sir? No? You didn't pay for this? You were put in this class, you didn't have a choice? I'm sorry. This one's worth mentioning. This is the one I was blathering about a minute ago. So here, this log 8 matters because when we plug 1 into f, we get 3 plus 5, which is 8, and that's equal to the constant term. When I plug 1 into the series, it's all gone. But the constant remains, and that constant has to match the log of 8. Someone here had log of 3 plus log of 5. That concerns me. I don't know where that came from, but I feel like it's not a good place. Like log of 3 plus log of 5 is not log of 3 plus log of 5. Let me say that again. Log of 3 plus 5 is not log of 3 plus log of 5, right? It's not linear. Anyway, I'm not sure how that happened, but whatever. Yes, sir?
Could you solve that by going 5 minus 1 plus 1, and then multiplying it out and combining that with 3? And then, like, if you divide by 3, you have log of 1 plus whatever.
I mean, could you add and subtract 0? I mean, that is what I did there. I just didn't write it like I have been.
So, when you took this.
See right here?
The derivative.
See this right here? What I've done is I've subtracted 5 and added 5.
Well, I was, because like on that one, you took the derivatives, used geometric series, which I guess, because in the problem, told us to use that, but like, could you have used like the natural log of 1 plus, like the Maclaurin series?
Oh, could you use the identity for, wait a minute. Oh, could you use the known series? Could you use the I got you. Your point is we have a formula, right? For, help me if I'm wrong. Log of 1 plus u is, what is it? The sum.
Negative 1 to the n over n plus 1 times n plus 1.
Oh, x to the n plus 1?
Yes, sir.
Yeah, u to the n plus 1. So you're like, well, I've got log of, what is it? 3 plus 5x. Okay. So I still need to do, okay, so that's 3 plus 5 times x minus 1. Make that 3 into an 8. Factor out the 8. Apply this result. Sure. Now, some of you were wrong here because you didn't leave your answer as a power series. So like I saw some of this, people had an answer like, I forget exactly, but something along the form of number times something like 5x minus 1 to the n. This is wrong. Maybe it's not wrong. Maybe it's equal to what you had before. It could be a legitimate step even. But that can't be an answer because a power series has the form, Cn times x minus the center to the n power, and that matters. Like, this is a power series. This is not. All right, it's something else. All of the theorems that I've given you for power series are true for power series. They're not true necessarily for slightly distorted versions of power series. It might be true for those. I don't know. Like the term-by-term derivative, integral, those kind of things. But all right, come on, computer. Too smart for its own good. Come back to us. You can do it. You can do it. Come on. Is there a way to turn off this pin thing? Anybody ever turn off the pin on their computer? No one ever thinks about disabling security features on their machines? No? Is that just me? Oh, they'll probably just tell me to put two-factor authentication on because they learned it in a class or something. All right, let's see here. Come on. Well, I was back on my machine. Now, let's try this. There you go. You recognize it now? Good job. All right. Somebody forgot to put the check for monitor flag and the reboot after sleep thing. Any other questions about the math battle? So yes, sir.
Can you go over one that was x squared over x plus 1
The x squared over this one, right? Yeah. So here, so like when I have something like this, x squared over 1 minus x squared, I look at it and I go, well, I can do that without that x squared there pretty easy. So I just ignore the x squared for a time, take care of that, and then come back and multiply by x squared after I'm done, right? So this is an important idea, like dividing and conquering, right? Like if I give you an example where I've got, one thing where you can easily, apply a substitution, and another one which is geometric, you might need to do two things at once, right? Like there can be problems which involve multiple techniques. This is sort of that, right? Because it involves multiplication by x squared and figuring out the Maclaurin series for the other piece. Now, the key idea here is that if we integrate 1 over the square, we get a reciprocal function, and then you can go geometric on that. Here r is just equal to x, yeah? And then I differentiate, kills the constant, right? It brings me to this. And then I multiply by x squared, and there's the answer. Well, almost. Again, that's not an answer yet because that's not a power series, right? It becomes a legit power series right here. Okay, this is not a big deal, all right? This is like you lose 10%, right? Giving me an answer like this, you're losing 30-40%. This is a more serious misunderstanding of what's meant to me. But anyway, I'm actually still happy if you've understood how to do it correctly, and it's just bookkeeping at the end, obviously, right? But go ahead.
Yeah, so like what if we didn't make that case of, what if we just never looked at it where you change, or you change indicate?
Oh, this is still a legitimate answer.
Okay.
I'm trying to
above that was.
I'm trying to illustrate the substitution idea, cleaning up answers.
Okay.
I would be content with that being an answer I gave you guys. I counted that as right for some groups. Yeah.
Not a dumb question, but how do you determine that m is equal to 1 on the bottom? Or is that given in the equation?
Oh, that came from differentiating.
That came from differentiation.
When I differentiated, my n equals 0 term dropped out. Going back up here. So there was an n equals 0 when we did the geometric for the derivative, for the integral of the function, but then when I differentiate, that n equals 0 term drops out and it changes to n equals 1. It was this step right here where that changed to 1.
So the only time it'll go up is if you take the derivative. Like if this, which is the term plus the first term.
I mean, if you integrate, the bottom index could go up.
Yes.
Yeah, that's possible.
What determines if n equals 1 or n equals 0?
It's a geometric series. I mean, there's different ways to write the geometric series formula. So the way I almost always have written the geometric series formula starts at 0, but there is a competing formula for the geometric series which starts at 1. See, you could either write, I'll write over here. Sorry, guys. You could either write the sum c r to the n equals 0 to infinity, or you could write the sum k equals 1 to infinity of c r to the k minus 1, like that.
And then when you say c, n to 0 drops out, what do you mean by drops out? Like fails class, or?
Well, dropping out is one way to fail a class, yes. But there are other ways, like don't come to class, don't do your homework, always copy homework from a friend. I mean, there are many ways to fail a class. But what was the question?
What do you mean? Why, when you said n to 0 drops out?
When we differentiate, this was x. The thing is, if you have c0 plus like c1x plus c2x squared and so forth, right? You differentiate this, right? And what happens? The derivative of the constant term goes away and you've got... So this one starts at n equals to 0. The one above starts at n equals to... Well, they both start at 0, right? But I mean, in both cases, the lowest order term is constant. But this is the sum what? N equals 1 to infinity of, n Cn x to the n minus 1, right? The thing I had up here to start with was the sum n equals 0 to infinity of Cn x to the n, right? So the index structure has changed. They both include a constant term, right? But the way the power function is indexed as it relates to the index is different, yeah. I should have a better word for that. I just don't at the moment. So let's see here. What do you guys need to know for the test tomorrow? Like what matters the most? Calculus 2 is a good answer. I haven't spent a lot of time talking about it, but the first, like, what, 20, 30% of your homework is what? It's the same stupid question over and over and over again, and there should be one of those on the test, right? If not more. What was that question? The IOC and the ROC, right? Figure out the interval of convergence and radius of convergence. There must be a question like that. Now, and also, situational awareness, right? You don't have to apply the ratio test when it's a geometric series, because what? Because the interval of convergence there comes from what? From the geometric series theorem we proved in the last test, right? That the radius, the absolute value of the radius has to be less than 1, right? Now beware, if it's a question where I say something, something kind of funny, like, I don't know, maybe I give you something like, f of x is equal to the inverse tangent of x plus 3 or something, and I say find the Maclaurin series for this and find its interval of convergence. Now there, you wouldn't have to apply the ratio test. You do what? You differentiate. It gives you 1 over 1 plus x plus 3 squared. You'd have some kind of, that may be a nasty question. I had to think about whether or not that's a fair question. Certainly if I make this a 3x, we're good. The x plus 3 I got to think more about. But anyway, so that, after you differentiate, it's something you can apply the Maclaurin series. You can find a Maclaurin series by geometric series, right? That will give you an interval of convergence. However, that's not the answer, right? Because then you have to do what? You have to integrate to get back where you went. And so you should be aware that when you integrate, you could change the IOC, right? So if then you got to check the endpoints. The open interval of convergence, but yeah.
Can you just plug the 3x into the non-Maclaurin series and then apply the ratio test? Or would that just be too much work?
You could do that, but if I say use geometric series techniques to derive the Maclaurin series for that, you can't do that. And I foresee myself doing that as that question has been asked. Thank you.
Pretend we can't read.
Well, it's always an option. I don't expect you to know the full binomial series, but I do expect you to know the first about 4 terms, I think. So for the binomial series, I think everybody should be able to remember this much. 1 plus, let's say, u to the alpha is 1 plus alpha u plus 1/2 alpha times alpha minus 1 u squared plus 1 over 3 factorial alpha times alpha minus 1 times alpha minus 2 u cubed plus dot 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 dot. By the way, the plus dot 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 is not optional. Not writing that plus dot 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 where it belongs makes your answers wrong. There was somebody on the math battle, you guys were missing your plus dot dot dots, and I've written that in. Like, that's not just that is, well, it is a passing comment. I don't think that's going to make you fail, but I mean, it's definitely something that I would be obligated to take something away from you if you didn't write plus dot 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 where it belongs. I have always written that, right? Anyway, yes?
What about when you're doing long division? You know you only need so many terms.
How do I know how many terms do I need? Or
If you're doing long division
with the plus dot dot dot?
you need a plus dot dot dot.
I'm more sympathetic to the omission of some plus dot dot dots in the midst of long division. I'm more talking about answers.
Right.
Yeah.
Yeah, I was going to ask, if it's the first 3 non-trivial, and you just write the first 3 non-trivial.
Sure, but the answer should have the plus dot dot dot, right?
Okay, I mean,
Yeah.
I understand that it's there, it's just it's the first 3
And, you know, I, as a point of clarity, try to write the plus dot 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 in my calculations too. You see it. Let's see here. What else can I tell you guys? The 5 Maclaurin series that you should have memorized are what? Yeah, exponential, sine, cosine, cosh, sinh. It's good, of course, if you know inverse tangent, log of 1 plus something, right? But I don't really expect you to memorize those, so if I ask about that, I'm probably going to ask you to derive it, or I'm going to state it, let you use it, you know. So I would expect there's, you know, division of series, multiplication of series, certainly Taylor's theorem's on the test, right? And I wouldn't be terribly surprised if I ask one of these calculate the 100th derivative of the function kind of questions, right, somewhere. There's probably going to be one of these ones where you reverse engineer the sum of the series by identification, right? Like we had some of those in here. The first problem, right? This thing. So you gotta go, oh, wait a minute, Maclaurin series, woohoo! So, in the wild, these problems are kind of more challenging because if somebody says calculate the sum of the series, there are 4 methods, right? It could be telescoping, it could be geometric, it could be a Riemann sum, that's a kind of more malevolent version, or it could be one of these, evaluate a Maclaurin series that you know. But sometimes the evaluate the Maclaurin series that you know, it can get a little bit more twisted, like if the Maclaurin series has, say, been differentiated or something. So there are variations on this theme which make it nastier. Although that didn't appear in your homework, so, you know, that would just be me being unfriendly or challenging you, depending on how you want to look at it. Other questions? What else do you need? You should, of course, look at the solutions to the, you know, where'd that thing go? If I can get to the right course, that'd be good. All right, come on. Come on, Canvas. So I have posted the solution to the, it's a lot of weeks, isn't it? Let's see here. No, I don't want you to open in that stupid thing. I hate this browser. I need to fix that setting. I haven't figured it out yet. I'll figure it out eventually. Let's see here. So we talked a little bit about these. Are there any theorems that we've covered this time that you should be aware of the proof of? There have been a couple. Yeah? What was the proof that we went over that is a proof that you could do? Because it involves nothing more than the ratio test and logic. Well, we did the geometric. That's true, but we did that last test. How about the term-by-term calculus theorem, that the interval of convergence for the derivative of a series is the same as the interval of convergence for the original series? I shouldn't say interval, but the open interval of convergence. In other words, ignoring the endpoints. You know. Now, I could only give that proof in the special case that all of the coefficients are non-zero, because otherwise we run into the sophistication of the Cauchy-Hadamard theorem and all that stuff, which I don't require you to know because it involves the lim sup, which is like, you know, above our pay grade in here. So, speaking of that, I was just talking to a friend of mine who works at the up in Dahlgren, the Naval Surface Warfare Division. They're looking to hire people. They're pretty much always looking to hire people. So if you guys are looking for a very boring government job that is hard to get fired from, it's a good place. So, no, there's interesting things that happen there. which I can't talk about here because I signed a legally binding thing to not talk about it. Let's see here. I'd say I'd have to kill you or something like that, but I don't have a gun really. Not here anyway. Let's see here. Not that I could have one here if I wanted though, right? Thank you, Liberty. Oh, yeah, that's a good candidate for a problem. The another one where we solve the differential equation, is that in here? Oh, so that problem 106 was unfortunate. Let's see here. What I was going to say is I would expect that there is a bunch of problems that are like find the first three terms that are pretty like low stakes in terms of credit, which means I expect you to be able to do them in like very little time. And if you've got your Maclaurin series, known Maclaurin series memorized, those should be a walk in the park. If you do that sort of thing with your GFA, I guess, I don't know. Let's see here. So what I was trying to get to here, and we're out of time, I know, but
No, the nav that sends it over.
this one here, I think problem 115 is nice because it's a combination of the last material and also the current material, in that, you're trying to solve this. You have to use a series method to solve that integral because we can't do any other way, Okay, anyway, that's all. I think you guys should be ready. I mean, we have had a stupid